So let's go ahead and get started. The agenda for today is to first review homework 1, okay? And I want to take as long on that as we need. So please do ask questions, and let's make sure that everybody's feeling good about that, okay? Then we're going to actually go into week 3 content, okay? So I have basically new slides, but it's the same sort of stuff that we talked about last week. But I want to review that content because I felt like, especially near the end, it was just kind of like, I have no idea what's going on for most people. Okay. So I do think that is super important content, and it's not something that you're going to necessarily always have to do, but it's a skill. And so like if you didn't get it at that time, that's completely fine. But it is a skill that I think is really worth trying to learn and trying to understand, because it will help you understand your models better. Okay, so we're going to go over that again. And again, please interrupt me if what I'm saying doesn't make sense. I'm going to show a little bit different function in terms of how to create data frames from which you would predict from your models, which I think is a little bit easier. I'm not sure why I didn't use it in the first place. Then from there, we'll finally start to jump into the new content. So we'll probably take a break after that point. And we're going to talk about the Gelman and Hill notation for multi-level models and how that differs from the Raudenbush and Breich notation that you're probably more familiar with. Okay, so I will explicitly, show the Raudenbush and Breich notation for a model, and then show the Gelman and Hill notation and how they are similar, how they're different, and why I prefer the Gelman and Hill notation at this point. Okay. And then finally, we'll talk about unstructured variance covariance matrices and alternatives. Because I've added so much up here up front now, I think there's a good chance that we will not get very far on that. And I'm completely okay with that. All right. So what I think I'm going to do, and it will really depend on what happens today, but if you look at the schedule going forward, I have a bunch of other stuff planned, right? But what I think I might do is kind of just slow the pace down, and so that we're actually getting the content and we're not just breezing through it all. So I may cut the lecture I had planned on simulating data from multi-level models. I will actually show you a little bit of that today, because it's part of the reason why I like the Gelman and Hill notation. But we won't. I'm thinking at this point that I want to cut that lecture just so we can slow the pace of everything else down. Okay, so we'll see how today goes. Today will be a big determining factor in that. If we get through everything today and we're feeling great, then we'll stay on pace. But if we, barely get into the variance covariance matrices, then I think that's what we'll do. Okay. All right. So learning objectives for today, there's a lot of them because of everything I just mentioned. So, but this is mostly just for the new stuff. And so again, I don't know how much of this we'll get through, but understand the basics of the Gelman and Hill notation and why I think that's preferable. You may disagree that it's preferable, but at least you'll understand why I think it's preferable. Gain a deeper understanding of how the residual structure is different in multi-level models from standard single level regression models. Understand that there are methods for changing that residual structure and why that might be preferable in certain cases. And then have at least a basic understanding of how to implement alternative methods. Okay. If you want to implement them, you have to use NLME instead of LME4. They're actually, Douglas Bates is a primary author on both of those packages. NLME is the older one, and it actually is shipped with R, whereas LME4 you have to install. So basically all the new development for the last 7 years probably has gone into LME4, but NLME still has some nice things like this, where you can change the residual covariance structure, which you can't do with LME4. There was a branch on GitHub initially to do this, but it never ended up going anywhere. Okay, any questions on that before I jump to homework 1? Okay. Okay, so I am going to jump into the homework. Let me switch my share. All right, hang on just a second. Okay. Back here, homework 1, index to homework 2. Okay. So after today, I will also actually post this to the GitHub repo. So I will show you a link where you can go and find that too. And like pretty much everything with coding generally, there are different ways that you could approach this. So I'll show you one way, and you may have done it differently, and that's completely fine. The important part is just that you got the structure right at the end. Okay, so I'm going to start by loading my libraries, load the tidyverse, load LME4, and then I'm also loading the performance package. Okay, and then down here, I'm first asking you to load in the data, and I just called my data L because it's longitudinal. Okay, so I run that. Notice I'm using here. So this is part of what's nice about the here package. Notice if you look at my file structure, I'm nested pretty deep here in my R project. But when I say here, it goes all the way back to my root directory, which is here, right? And I know that because I have this .rproj. It goes all the way back there, and then it says, okay, from here, the root directory of your project, wherever that .rproj is, go into data and then load that data from there. Okay, so that's how here works, even though my actual thing I'm running here is clear down here. Okay. So hang on just a second. Is there a way to preview what you get with knit without having to run knit? So I tend to actually just run things interactively here, right? So like I look at them here or whatever. There is actually in the newest R Markdown, I don't really want to do it right now because I'm worried that, well, I'll just try it. There's this little button right here. As long as you have the newest R Markdown, it's this visual editor, and it will, yeah, switch like this. And then it will look like how it will when you render at the end. So if I click L there, oh, I guess not. I don't know. Maybe I have to click this button. No, I have my settings so it all runs down here. So, so that's one way you could do it. Otherwise, I would just probably click knit a bunch. The problem, so you can click knit like 800 million times and it's not a problem. The only thing is sometimes if you have chunks that take a long time, then you don't want to be clicking knit a bunch of times. So there's kind of two ways around that. One is you can use caching. So I've set cache equal true globally. So for all of my chunks, it will cache by default, which means I'm going to end up with this index underscore cache over here. Okay, and it's called the index because my file is called the index. But what that will do then is when it's running a chunk, if there's a cache file associated with it, it'll just go and grab that result rather than rerunning it. So that can really help speed things up. It also ends up with problems though, and I actually had a problem with this one because I had initially messed up the way that I had coded time. And I didn't realize until yesterday when Sarah pointed it out to me that my figure was actually wrong because it was coded using that incorrect coding because I had fixed the coding in that code chunk, but that chunk that was rendering the plot didn't get updated because of the cache. So you can run into issues like that too. So you do have to be a little careful with it.
Daniel, can you say really quickly, I see in that line 64 that you have include equals true, but also in your or up globally, you have those set as echo equals false, message equals false, warning equals false, include equals false, but then you also did that in your code chunk.
Yes. So right at the top, when you do, new R Markdown, you'll always get this knitr ops chunk set. This is your global options for the R Markdown. So right in here, you can always add additional arguments for that specific chunk. But right here are your global options for all chunks in the document. Okay, so for me, I'm saying echo equals false globally because I don't generally want my code to be echoed. Occasionally I do. And so for those chunks, I will override that default to say echo equals true. And include equals false means like by default, none of those chunks are going to be included at all in the output from them, whatever. But they will run. Message false, like all of these are my defaults. And then when I get down here, like this is one where I wanted it to be included. And so I say include equals true. And you can read more about the default options, the chunk options online. eWay has a whole bunch of documentation about all of the different options. But generally, the main ones are going to be echo eval, which is whether the chunk should be evaluated or not, message warning, and then include. But include is less important than those other ones because you can actually replicate include with all of the other things. Does that make sense? So this sets your chunk options globally, and then you can always override those here with a specific chunk. Any other questions so far? Okay, so I have my data set and it looks like this. And I probably didn't do a great job of explaining this here, but I did want you to code it by season 0, 1, 2, but then you have grade. And so there's kind of two different ways you can think about this. You could think of it as 0, 1, 2 within each grade, or you could think of it as one slope for one student that goes from 0 to 8. So one slope across grades. And that was actually what I was hoping you would do. And so I wanted a wave column that was coded by season, so 0, 1, 2, but for each grade, so it would go 0, 1, 2, 3, 4, 5, 6, 7, 8. So a numeric column, okay? And then also have a grade column, and I wanted grade to be a factor because I wanted it essentially to be dummy coded. So you would have, say, grade 3 as your reference group, and then you'd have a coefficient for grade 4. And then you'd also have a coefficient for grade 5 that would compare grade 5 to grade 3. Okay, so that's what I was looking for. So the way I ended up doing this, and again, I wouldn't expect that this is necessarily how you would do it, but it's one approach, is I just wrote this little function called create wave. Okay, so here it takes one argument, x, and I'm saying case when x, whatever x is, right, is equal to fall, then 0. When x is equal to winter, then 1. And when x is equal to spring, then 2. Okay? Then with my, so I'm going to run that real quick. Then with my pivot longer, I have L, right, again, that looks like this. And then I'm going to pivot longer. So I'm going to say it starts with G. So all of these are going to be moved to 2 columns, right? These are going to be the names, and then these are going to be the values. Okay, so I'm going to say the names are actually going to go to 2 columns, grade and wave. Okay, and I can do that because I have this separator between them. And I probably should have said grade and season, but the difference is, the reason I said wave is because of this transformer down here. So I'll talk about that in a second. But so I'm taking all of those ones that start with G. I'm saying the names are going to go to grade and wave. The values are going to go to score. There's a name prefix, which is G, right? So I'm going to basically drop this G from all of them. So it'll just say 3, 4, 5. And then there's a name sep, a separator, right, in the names, which is that underscore. So this underscore is going to separate that column that would just be a single column into two columns. One that I'm calling grade, which is just going to be 3, 4, 5, because I'm dropping the G with the names prefix. And then one that's called wave, which is going to be fall, winter, spring. Okay? Then finally, on this names transform part, I'm passing it a list, and I'm saying for wave, apply that function create wave. Okay? And then for grade, I'm saying factor. So I'm saying make grade a factor. Okay? And when I run just that part, you'll see it looks now like this. District ID, school ID, student ID, grade, and it's a factor, wave 012, 012, and score. Okay? So then the last part is I just want wave to, instead of being 012, 012, 012, I want it to be 012, 3, 4, 5, 6, 7, 8. So that's what I'm doing here in this last part. I'm saying wave, if else, if grade is equal to 4, then add 3 to wave. If grade is equal to 5, then add 6 to wave. Okay, and there's other ways you could do that too, of course, but that was just the way I thought of as I was doing it. Okay, so then I end up with something that looks like this. Yes.
The names prefix argument, if you use that, because you're putting this to two name columns, I would expect it to want two arguments there. If you had two different prefixes, can you give that a list?
That's a good question. I have never done it like that. I've always just used names prefix on the overall names.
Okay, interesting.
So I think the names prefix is actually being applied before the split. Like that's
Gotcha.
kind of how I have them ordered here in my arguments, but that one wouldn't matter, of course, what order you supply the arguments. But that's kind of how I think of it in my mind, is that like the prefix comes first and then the separation. But
okay, thank you.
I'm not sure if there's a way around it. Any other questions? Okay. So this is how I would expect your data set to look. And again, I wouldn't necessarily expect you to take this approach. This is a approach that you could take, but you could have used a bunch of other different methods as well, as long as you ended up with something that looks like this, right? And the column types are very important here too. Okay, and then part A with model fit. Another thing I learned while you all were going through this is that I think I use a little bit different language than Joe might have, or than many of you are used to, because I think what I was asking for here was maybe a little confusing at times. And specifically, it's the use of this term, I think, unconditional growth model, because I know you've all talked about unconditional models, but what I'm referring to when I say unconditional growth model is a model that has time or wave or whatever in there, some sort of thing that's indexing time, and that's it. Okay, so then you are modeling the growth, but the growth is unconditional. There's nothing that is predicting the rate at which students are going to grow or progress over time or anything like that. Okay, so an unconditional growth model with random intercepts and parallel slopes. So that means every kid is going to have their own starting point, but everybody's going to be assumed to progress at the same rate. Conditional growth model with random intercepts, parallel slopes, and grade level fixed effects. So this is going to be the exact same model as this, but we're going to include a fixed effect for grade. Okay. Then unconditional growth model with random intercepts and random slopes. So now every kid is going to have a different starting point, and their rate at which they progress is going to be different. And then that same thing, but with a grade level fixed effect. Okay. And then I note here that when I ran models 3 and 4, I ran into some convergence issues. I think I have a note in the slides this week about ways to deal with convergence issues if you run into them. There's a command called allFit. I can actually show you real quick, but that'll help you see what optimizers are actually working, if any. And you can also compare how the estimates would change across optimizers. Okay, so I'll show that real quick here. But this is how I did the models. So I called them M0A and M0B because they're both unconditional, or no, this is this conditional model, whatever. I don't know why I did this. These should have both been unconditional because M0 usually means unconditional, but that's not what I did. Anyway, So M0A is the unconditional model with random intercepts. Okay, so that's what this is specified here. Random intercepts across students, but parallel slopes. Okay, so in other words, we're estimating one parameter here for wave. Okay, we have a coefficient for wave, and there's only one of them. So every student is assumed to progress at whatever rate that coefficient is estimated at. I could be a little more explicit here if I wanted to and say 1 plus wave, and that might be helpful as you're getting started because it makes things really a little bit more clear. Score is the outcome, right? That's modeled as a function of 1, which is the intercept, plus wave, okay? And everything that comes there is your fixed effects. Those are the fixed effects that you're estimating. Then you say plus, and then you put in parentheses the things that you want to randomly vary and the thing that you want them randomly varying across, okay? So I want my intercept to randomly vary across SIDs, okay? So the random effects are always specified in parentheses, and you always have to the left side of the bar, you have the coefficients that you want to randomly vary. And then to the right side of the bar, you have the group that you want it to randomly vary across. Okay? And that's how you're always going to specify random effects. So I can run that, and it takes just a second, and it's done. And then M0B, I'm going to say the same sort of thing, but now I'm including grade right there. And that's because I want grade modeled as a fixed effect, but it's not a random effect, okay? So grade is here, all right? And we can look at those model results if we want. Oops, 0A. So here's the model with, let me bring this up a little bit. Here's our model with random intercepts and parallel slopes. So we can see students began on average with a score of about, oh no, that's variance. They began on average with a score of about 190.5, and it's 190 because this is in scientific notation, right? And they progressed on average about 3.67 points per wave, okay, which is per season, okay? Their intercept, 190, varied between students with a standard deviation of 12.3. Okay, and then the residual standard deviation was about 6. Okay, we can do that same thing, but now let's look at B, and you can see we have an initial student started in grade 3 fall with an average score of about 188.8. They progressed about 6 points per wave. And then these coefficients maybe don't make a lot of sense when you're first looking at them. -8 for grade 4, -16 for grade 5. And the reason that is because of the same sort of thinking about how the model is working, right? How the model is making its prediction. These things do not come in until later waves, right? So grade 4 is going to be 0 during grade 3, 1 during grade 4, and 0 during grade 5. Okay, so that means once this grade 4 comes in, we're going to be 188 plus 3 times 6, which is 18, right? Minus 8. So basically what we've got is kids are growing during the year, and then we have summer between years, and they drop from the end of the school year to the start of the next school year. And then they progress again, and then they drop again. And so that's what this is. So now for grade 5, right, it would be 188 plus, let's see, 3, 4, 5, 6 times 6 minus 16. Does that make sense? Okay. All right, then M1A. So I'm going to run this without this optimizer real quick, and you will see that I get convergence warnings. Right? So I get this convergence warning. So I'll talk about that in just a sec, but I should walk through the formula first. So this part is all basically the same. The only thing that is different is now I have wave randomly varying across SIDs. Okay. And so the reason that this is working is because grade does change, right? Like this, the column grade changes within each SID. So therefore, it can randomly vary across SIDs. If I had something like, let's say, the you know, the gender that the kid identified as, if I had that as a column in my data set, I would not be able to have that randomly varying across SIDs because it would be constant within a student, right? Or at least for most students, we would assume it would be constant. Okay, so you could not estimate that as randomly varying across student IDs, but wave you could because it's going to change within a student. Okay, so now we have, this is actually like this, right? And same thing over here. And one other thing I will mention is that your random effects here should always be fixed effects here, right? So you shouldn't have, you can have fixed effects that are not random effects, but you shouldn't have random effects that you're not also modeling as a fixed effect. Okay. All right, so I mentioned I got this convergence warning. One of the things I could do, I'll just create an object called A. I could use this function allFit, okay? And then I'll say M1A. And this will take a little bit of time, maybe too much time for us to actually go through. We'll see how. No, it's going to be fast enough. But what it's doing is it's going to go through a whole bunch of different optimizers. I think there's like 6 of them. And it's going to fit the model for each of those optimizers. And then we can look through and see if there's models where just using a different optimizer fixes our convergence warnings. Okay. But the other thing that we can do is once this is done, we'll be able to look and actually see the coefficients across optimizers. And most of the time, in my experience anyway, the convergence warnings are sort of false positives, right? It's like you're getting a convergence warning, but it's just because it's not reaching some arbitrary threshold tolerance, right? And if you look at the actual estimated parameters of the model, they're almost exactly identical. So now we can call summary on A, and we get a bunch of different stuff. This is a list, right? Most of this stuff we probably don't really care about too much. It's how long the model took to fit, which is useful. But theta, so this is like this sort of ending part for the random effects, and you can see those are all darn near identical, right? The standard deviation and the correlations. So this is what the intercept variance was estimated at across models, incredibly similar. This is for wave and intercept, so this is a covariance. This is the variance in wave, and this is the estimated residual variance. Okay, all super, super similar across them. This is the log likelihood, so what the log likelihood was at when the model converged. Again, super, super similar. Here's the fixed effects, they are identical. And then here's these messages, right? So now I can say, all right, so for the messages, this optimizer, which is the one we ended up using, does not have any messages. It converges fine, and it doesn't complain at all. Same with Nelder-Mead, same with this one, same with this one. And then these 3 down here give me these convergence warnings. All right. So if I use one of those, I'm going to get a convergence warning. But as we saw down here, it really doesn't matter anyway, right? The results we get are darn near identical. And we're probably never going to go beyond 3 decimal places of reporting anyway. So it's a way to inspect your model if you're getting convergence warnings. And ideally, you can just switch your optimizer and you get it's like a get out of jail free card, right? You don't have to worry about anything. So that's a really good strategy. Okay, and then the last one, this is going to be the same sort of thing, but now I'm just including wave as fixed effect. Okay. Any questions on that?
I have a quick question about the optimizer.
Mm-hmm.
Can we when we are reporting those results with different optimizer, can we just say we fit using different ones, but doesn't it cause any problem, or it's just fine if we are explicit about it?
I think it's totally fine. I don't even, if I was able to run the model with something other than the default optimizer and I got no convergence warnings, I'm not even sure I would report it. I always try to make my code available with my publications so somebody could look at that and they could see that I used a different optimizer, but there's nothing special about the default optimizer, right? And you're still using maximum likelihood. It's not a difference in the estimation. It's just a difference in how it basically tries to find the maximum likelihood. So you could put it in a footnote or something, we use the Bobiqua optimizer or whatever, but it really, like I said, there's nothing special about any of these optimizers relative to any of the other ones. The important part is that you're getting the maximum likelihood.
Thank you.
Mm-hmm. Any other questions? Okay, so then this next part, I asked you to compare the performance of models. So some of these take a little bit of time, so I'm probably not going to run all of them, but you can use compare performance across all models. And then I ran things like this too, so just comparing model 1A and model 1B. And this still takes a bit of time. All right, I'm just going to stop that. Maybe. Oh, shoot. Maybe not. Okay, so yeah, all right, there we go. I don't think I got that. Yeah, okay. So, but one other thing you can do is you can just compute the difference in the AIC and the BIC. So this is after this, right? But this is model 1A and model 1B, so I was computing the difference between the AIC and the BIC between those two models. And test performance, test likelihood ratio, right? All of these things are just basically different ways of comparing models. And then you can also just do ANOVA, which it's going to, this is probably why the other one was taking so long. You have to use maximum likelihood instead of the default, which is restricted maximum likelihood to compare across models if you want to do this chi-squared significance test, right? So this is saying model 1B fits the data significantly better than model 1A, as shown by the change in the log likelihood with a chi-square test. But more important than that, I think, are these AIC and BIC values. And you can see both of them are considerably lower for M1B. So we would probably conclude that that's the right one. I also had you install this Sundry package, or I put out an announcement to install that for next week, I think it is. No, it's this week. And so there's another function in there called AIC weights that you can use, where it'll just pull the AIC values, and then it'll compute the delta, which is like the difference between the AIC values. And then it'll give you these weights, which are like, if you have models that are close, it'll be like, essentially, this model has like a 70% chance of being closer to the true data generating process than the other. And so in this case, you're getting a 1 for this one, which says this model is just fitting the data much better than the other. Okay.
Dan, I have a question.
Given by AIC. Yep.
So you're like throwing out a bunch of stuff here that like I was trying to either do by hand or just didn't know to do. What's your recommendation now that I did it one way, I see you did it another? I know you're going to post this. We go back and grab the code and re-put it in our homework and rerun it to fix, like, because there's like you're introducing new functions here that I think are really super helpful, but like, just what's your 2 cents on what to do now that we're seeing this stuff?
Yeah, so these I don't think these are new. These are all ones that we talked about last, or during the second class, I think it was.
I think I just missed the diff then. I missed that diff perform.
Oh yeah, so like diff I didn't talk about, but this is,
and then Sundry, I didn't see Sundry.
Yeah, Sundry wasn't in there either, but diff is just this. This is just a fancy way of doing this.
Yeah, I just did it by hand and didn't know those.
minus, or actually it'd be like, yeah, no, 1 minus 2. Like that's all it is. So I wouldn't worry about that at all. And this AIC weights one, I didn't include because originally I was not going to have you install that package, but then I ended up writing a new function so that we could pull residual variances out of LME4 models. So then I had you install it anyway. So that's why I showed it here. So that one's also not that big of a deal. I would focus more on ANOVA and then these test performance, compare performance, test likelihood ratio, all those functions from the performance package. But again, even across those, I would probably focus mostly on the AIC and BIC values. To me, those are the most important things. Other questions? Yep, Chris.
I have one about using the AIC to compare and also this function. So when we do the chi-square test, they're supposed to be like nested models. So like the variables that are in them should be the same and we can parameterize them differently. But with this AIC weights and stuff, could I use that information of that weight column in a model that was not nested?
Yes. Yeah, AIC and BIC can be compared across non-nested models.
Okay.
Any other questions?
A quick question. Is there any special reason why you only compare 1A and 1B, but not the other two?
It's just because up here I did compare them all and I tested them all here, and M1, both the M1s with the random slopes were better, I think.
Yeah, thanks.
So then I just have this like sort of summary here. So I said when comparing across models, most complex model was the best. And then I use some indications of AIC and BIC values, both for 30,000 points lower, which the sort of rule of thumb is 10 points, right? And so these are 30,000 points. So it's like not even close. And the chi-square test was significant. And then I cite some of that information. Okay. Okay, finally, provide a brief write-up interpreting your model, and then we're going to do the plot too. But so I did summary here to start, right? And then I just wrote up some stuff. This conf.int I'm definitely not going to run right now because it takes a long time to run, as you probably saw. Depending on your computer, it might have even taken like 10 minutes, right? Because there's different types of confidence intervals, but the ones I've recommended you use, because you'll get confidence intervals for the random effects also, are, or for the variance components rather, are either profiled confidence intervals, which is what this is computing by default, or Bootstrap. Okay, Bootstrap's probably better, but they're even more computationally intensive. Okay, so then I just have some information here, right? Students scored on average 188.79 points in the fall of grade 3, because that's what the intercept represents, right? Given the way we've coded WAVE. And then I put the 95% confidence interval there, which varied between students with a standard deviation of 10.14 points. Apparently I'm getting slightly different numbers this time, not sure why. Students gained on average 6.18 points, right? Which varied between students with a standard deviation of 1.34. Oops, I cited the wrong thing there. So that should have been 1.16, unless maybe this is, I'm showing a different model here. I'm not sure. The coefficient for grade 4 indicated students lost on average. Yeah, this is different. I don't know what I did differently, but 1.99 points from grade 3 to grade 4. So this should actually be 8 points. This might have been when I had my WAVE coded messed up, but that's what it is. The coefficient for grade 5 was a bit more difficult to interpret. Had students continued on their average trajectory during grade 3, their predicted achievement in fall of grade 5 would be 188.79 plus this times that, which is 228.5. However, students actually scored 10.51, which is actually 16.69 points less than that amount. Okay, I will, before I post this, I will update this with the correct numbers, because I think this was from when I had accidentally messed up on coding WAVE, and that's why all those numbers are messed up. Questions on any of that though? Okay. Finally, I'm asking you to produce this plot. So there's, again, multiple ways to do this. By default, your predict function for a model is going to give you your predictions for every single observation in your data set, okay, for every row. So what I'm going to do, the way I did this, is I just started out by creating a new column called pred, which is just predict M1B. Okay, and I don't have to specify new data or anything because because L is the data set that I used to model it. And so when I call predict, it's just going to predict for every row of that data set. Okay, so I do that and I get that. So here's my observed score. Here's my model prediction for every student. Okay, then I'm going to filter where SID, right, is in, and I'm using different SIDs than you did, but those three. So now my data set is only 27 rows long. Then I'm just calling ggplot and putting wave on the x-axis, score on the y-axis, and then I'm putting a layer of points. Okay, and then I'm saying add a line where now I'm redefining the y-axis. So instead of the y-axis being score, it's going to be pred. So I'm going to put pred as my y-axis for this layer, which is the lines. Okay, and then I'm changing the size and the color. And that doesn't look very good because I need to facet wrap by SID. Okay, and then after that, the rest is just theming stuff. Okay. Questions? All right, so I will get those numbers updated and I will post that later today, probably. I have another meeting from 1 to 5 today, unfortunately, so that's the only potential hiccup in there. But I'll try to get it posted today. If not, it'll be Monday.
Could you switch the SIDs to what we were supposed to plot, 1, 2, and 3, when you put that up too, just so I can make sure that's the same?
Yes, I will do that as well.
Okay. I noticed that you put the deadline for this assignment is tonight at midnight. Is that what you intended, or you want before the class? Yeah, I submitted it, but anyway, just want to check.
Yeah, so generally I'm going to review them on the day that they're due. But you know, the deadlines, as I've said before, is like totally up to you. Whenever you need to get it in is fine. But I'm generally going to review them on the day they're due. So if you'd like to you know, be here during that time and go through it with me, it would be ideal if you had it done before class.
Thanks.
Yeah. Yes, kind of same question. I realized I didn't code my grade as a factor and it was left as in numeric form. So now I'm wondering if I should kind of go back and do some of the revisions or just keep it submitted.
Yeah, it's totally up to you. You know, I'm probably not going to be taking off points for things that you did incorrectly anyway, unless you did something like super wrong, like didn't get finished with it. Like if you just straight up don't do something, then I'll remove points. But if you're trying and it's just not totally correct, like something like that, which especially like that is partly on me too, because I didn't communicate that clearly enough, I don't think. So I won't remove points for that, but if you would like to go back and do it so that you can replicate the results more, then it'd probably be helpful for more practice. So.
Okay.
Other questions? Okay.
Just a quick, sorry, just a quick one about reporting. When we are reporting the final results, do we report on AIC, BIC differences in the model that's fitting best? Or do we just say this has got the lowest value?
I would report on the actual differences, yeah. So, so whatever models you're comparing, I would actually either state the AIC and BIC values for those models or state the delta, right? The difference in the AIC or BIC values for those models.
Yeah, and also when I was, the way I compared models, I just simply did ANOVA, and that gave log likelihood ratio as well. So yes. I do not need to separately run log likelihood.
Yeah, so there are slightly different tests. That's partly what I ran into. I think it was last time, or maybe it was the time before that. I think it was the time before that. there's the likelihood ratio test, and then there's which is a ratio test, and then there's the testable log likelihood or the deviance or whatever. There's quite a few tests that are slightly different. My main approach to all model comparison stuff is just to look at it as many ways as possible, basically. And you know, as I mentioned before, I would think of it in terms of model comparison, not in terms of model selection. So, you know, even if your evidence is pretty clear that one model is fitting the data better than another, you still probably want to be careful because you still always have a sample, right? And it's not the end all be all. But the evidence for your sample with the model that you fit suggests that that model fits better than the other models, but it's always relative too, right? There could still be another model out there that fits better, but in the set of models that you're comparing, this model displays the best fit.
Yeah, thank you.
Mm-hmm. Okay, any other questions? Okay. So we are going to review week 3 content now for the next little bit. And then same with the review of the homework. I would really like to take whatever time we need here to do this, because I do think this is super important. So please feel free to stop me if what I'm saying doesn't make sense. Okay? You can go ahead and follow along here as well. So this is the data and the model that we're going to be working with. I'm loading the tidyverse and LME4, and then I'm reading in the popular data, okay, which we've worked with previously. This time I'm fitting a model that's slightly different though. I have popular as the outcome, and then I have modeled by Xtrav, etc. Okay, so what I'd like you to do is go ahead and fit this model, but then look at it and tell me in plain English, what is this model fitting? Like what's actually happening with this model? Xtrav is a measure of extroversion. Then give me a thumbs up emoji when you've got that going. And again, you can always just copy the code. That's totally fine. All right. Looks like about half of us. Give it another minute or so. Okay. All right, so somebody volunteer. When we're looking at this model, what is this model actually fitting? Like, what are we doing here?
I can try.
Okay.
So it's saying something like being popular as a function of intercept and extraversion, and intercept and extraversion are randomly varying across level 2, that is class, in our data set popular.
Very good. But what does that mean, the extroversion and intercept are randomly varying across class? What does that actually mean?
We want to see how these are changing as per different grades in our data set. We have level 1 variable as well as level 2. So grade is level 2 here. So we want to see how every grade is impacting students' popularity.
Right. Although it's class, not grade, right? That's the only thing. But yes.
Sorry, class, yeah.
Yes. So basically, we have, rather than saying we're going to fit a slope that models the relation between extroversion, if you think about it as a scatter plot, extroversion on the x-axis and popularity on the y-axis, right? Rather than having one slope, we're going to have a slope for every class in our data set. And because we're allowing the intercept and Xtrav to randomly vary across class, that means not only is the intercept randomly varying, but the relation between XTRAV and popular is also randomly varying between class. So you could imagine in one class, maybe the teacher lets them get away with a lot more, and so kids who are more extroverted are more popular in that class, versus another class where a teacher is very strict and everybody has to be really quiet all the time, and so it doesn't matter if you're extroverted or not, your popularity is sort of independent of that, right? So we're saying your popularity depends on your extroversion, but the effect of extroversion on popularity is going to depend on which class you're in. Okay, that's one way to sort of think about it. All right, so this is what this is going to end up looking like. So I have, I'm saying that students had an average, students with 0 extroversion had a popularity, average popularity of 2.46. For every 1 point increase in extroversion, students' popularity increased by 0.49 points on average, okay? The intercept, so students' extroversion at students with extroversion of 0, their popularity varied between classrooms, not between students, between classes, with a standard deviation of 1.73. And that relation between extroversion and popularity varied between classes with a standard deviation of 0.16. Okay? All right. Let's compare this as just as a way of sort of thinking through what this model is doing, how it's working. Let's compare it to simple linear regression. All right. Oops, I jumped forward a bunch. So this is how we would fit the model in R with simple linear regression, right? So I'm just calling it SLR, and this part's all the same, but we don't have that random effect structure, right? And here's our coefficients. So visually, this model looks like this, okay? And this is what I was mentioning before. We have now one intercept, which is here, and then one slope. And our prediction is going to be the same for all students, right? This is how we would predict for those students, right? We would say your baseline popularity is going to be 3.27. And then for every 1 point of extroversion that you have, we're going to add 0.35 points to your popularity score. And that's going to be as good as we can do. So for scores of 0 to 5, it would work like this, right? For 0, we're going to go 0.35 times 0, which is going to just be the intercept, 3.27. And then for a point of 1, we would add 0.35. 2, we're going to add 0.35 twice, etc. Right? It's a line.
Daniel, sorry, can I ask just one simple, clarifying question? Mm-hmm. When you're talking about the fixed effect of the 0.49 estimate for extroversion, is that at the student level or the class level?
So it's that's still at the student level,
Okay.
Like back here, 0.49. Yes. So this is at the student level because the data is at the student level, right? So students are level 1 in this analysis, yeah. And class is level 2. But this is like average across students.
Right. Okay.
Because it's a fixed effect. Right?
Okay. Yeah. Thanks.
Mm-hmm. Okay, so this is how we would make predictions with a simple linear regression, right? We just have this extroversion score, and we're adding whatever that coefficient is, we're multiplying it by their extroversion score, and we get their predictions. So we're fitting this line, right? Okay. Now for the multi-level model, it's a little bit more complicated, okay? Because each class has their own intercept. And you can think of that as an offset. This is the way I think of it anyway, as like an offset from the overall intercept. Okay, so you have this like sample intercept, and then each class has their own intercept, which is just the difference between that overall intercept and their intercept. Okay, and every class has a different slope. Okay, so again, we have one slope, and then we have the difference in that slope between the overall slope and the slope for the specific classroom. Okay, and then that's for kids that are in our sample. But there's cases where, you know, what if, say, we had we wanted to make a prediction for a kid in a different class, like we have a new teacher that's coming and they're going to teach in the annex. So it's like literally a physically different classroom, and it's a different teacher. Okay, and we want to make predictions for those kids. How would we do that? Well, we don't have an estimated intercept or slope for that class. So then we would just use the fixed effects. Okay, so let's walk through four predictions. What I'm going to do here, and you can copy this code if you'd like, but basically I have popular here. I'm going to group by class, and then I'm going to slice 1. So that means I'm just taking the first row for each class. Okay, then I'm going to ungroup, and I'm going to slice again to take 1 through 4. So I'm just taking the first 4 rows of that data set. So what you see I get here is the first student for each of the first 4 classes. And this is an instance where you can see the IDs repeat across classrooms. So pupil 1 in classroom 1 is different than pupil 1 in class 2. And we can see that very clearly because their extroversion scores are different, their sex is different, their treatment exposure, I guess is what that is different, and their popular teach is different, right? So all the data is different. So these are clearly different students, but we just have this in each classroom, it goes 1 to n, okay? So we're gonna make predictions for each of these 4 students, okay? So our coefficients look like this. This is using the Gelman and Hill notation that we will talk about more in a minute. But basically, this is our average intercept, and then this is our slope. But then this slope randomly varies. This intercept and this slope randomly vary, right? So we have this intercept variance here. We have the slope variance here. But we also have the correlation between the intercept and the slope variance. Okay, we actually don't have to worry about this too much because we can just extract that from the model. So what we're going to do now is we're going to make these predictions by hand, but we're going to do them by hand by sort of pulling out pieces of the model. Okay, so I'm creating a thing here I'm calling f, which is the fix f. Okay, fix f is a function from LME4 from m. So this is saying give me the fixed effects coefficients from the model that I fit, m. Okay, and I get these 2. The classroom deviations, there's a couple of different ways we can do this, and I showed you a different approach using broom.mixed last time, or parameters. But this time I'm just going to skip all of that, and I'm just going to use straight from the LME4 functions and say, just give me the ranf from m. And part of the reason I didn't do this before is because the structure of this thing can be a little bit complicated. Okay, you see we got this $ class thing here. That's because when I call ranf, what it returns is a list. And this makes the most sense because we often have multiple grouping levels. So let's say we have class, let's say we also had school. We would have a list that has a class data frame like this, but also a school data frame. So we'd have to pull out which ones we want. Okay, and then the row names are the IDs for those classes. Okay, so these are the random effect estimates for the first class. These are the random effects estimates for the second class, etc. Okay. Now we're going to make our predictions. And because we've modeled these random effects, our predictions now depend on classroom, which is very different from simple linear regression, right? Where you're just making the same predictions for everybody. The fixed effects part works just like simple linear regression. So here is the first student from sample preds that we're going to make a prediction for. Okay. So our popular, we're going to first start out with the fixed effects part. 2.46 plus 0.49, those are our fixed effects, times 5. Why times 5? Because that's what this student's extroversion score is. Okay, so that part's just like simple linear regression. There's nothing different at all. But now Oh, and we can see this is just confirming that what we calculated here is correct. And you can see we have rounding differences because I only rounded these out to 2 decimal places when I did this part. But F1 plus F2 times 5. Okay, and these brackets, in case you're not familiar, the brackets pull out the parts of the vector. Okay, so F is here, right? It's a vector of length 2. And when I use those brackets and say 1, it's just going to give me this one. And when I use the brackets and say 2, it's going to just give me this one. Okay. All right, so F1 plus F2 times 5, that gives me the fixed effects portion of the prediction. But now we have to add in the random effects. Okay, and we have to make sure we get the random effects for that specific classroom. So here I'm saying our $ class, which is a little bit more complicated, right? But that's because of that list structure. But that's going to give me, this head is going to give me the first 6 rows of a data frame. And when I say our $ class, it will give me the data frame for class. Okay, so here's the random effects. And now what we end up doing is we just extend that prediction that we had before to include those pieces from the random effect. So we have 2.46, that's our fixed effects, plus 0.34, right? Because that's the difference for this classroom's intercept and our overall intercept. And then we say plus 0.49, the overall slope, plus a negative 0.03, because that is the slope for this classroom. Okay, and then we multiply that by 5 because that's what the student's extroversion score was. And we get 5.10. Okay, we could do this in code like this. So class 1, I'm just saying our class, and then I'm saying give me the first row for all columns. Okay, that's why that's empty. First row, all columns. And I get class 1 like this. This sort of notation is not particularly important, but I do want to walk through it with code too. And then we would do it like this, right? F1 plus class 1, 1, plus F2 plus class 1, 2, times 5. And we get this prediction, 5.131195. And that's our prediction for that student. Okay, we will confirm that that is correct here in just 1 second. Okay, now let's think about these first 4 students again. Okay, so here's the first 4 students. Here's the random effects for those first 4 classrooms, right? So 1, 2, 3, 4, you can see are the row names here. And we have classrooms 1, 2, 3, 4. So these are the random effects for these 4 classrooms. And here's the fixed effects, which are going to be the same across classrooms. So to make these predictions, this is just like simple linear regression, except we include those random effects. Okay, so 2.46 plus 0.34 for the first classroom, plus negative 1.18 for the second classroom, plus negative 0.63 for the third classroom, etc. Okay, so this part is changing because of the random intercept, right? And similarly, this part is changing because of the random slope, right? And then finally, this part here is just what the student's extroversion score was, 5853. And we end up with these predictions, okay? We can also get predictions for just these, students by saying predict from M, where the new data is equal to sample preds, which is just those first 4 students, first from each of those first 4 classrooms, right? And we get something that looks like this. So notice the first one's off a little bit because I rounded this one quite a bit, I think, or no, I don't know, one of them, I can't remember which one. The rest of them are all rounded as well, but it's this one because it's negative 0.027, right? The rest of them were close enough that our rounding ends up being quite close, and we're basically there. Okay, and we could replicate these with code, as I did back there, and you'll see we get exactly the same thing, right? So here, 5.131195, 5.131195. Okay? So that's how we're going to make predictions with a multi-level model for our own data. But what if we want to make predictions on new data? data that we have not seen previously, okay? That's where we use only the fixed effects. And then it's just like simple linear regression again. And the reason is because those fixed effects are our best guess for like the population level estimates. And we're not going to include a random effect for a given classroom when that classroom has never existed before, right? We have no idea what that classroom is going to be like, so we just use the fixed effects. Okay, any questions on that before I move to this part?
Is that, I have a question about the random intercepts. Is that basically like what's used to calculate like value added scores for teachers?
Yes.
Yeah.
The value added scores are often actually fixed effects models though. So there are basically just like a vector of teacher IDs that get dummy coded into this big thing, and then you have fixed effects for all of them. But there's a whole bunch of different models, but yes, that's basically it. They're often random effects models as well. So.
But the fixed effects one would give you like the difference between like the reference category. So they're not using like the coefficient that comes from like dummy coding every single teacher.
Well, so it's basically, yes. Either way, they're essentially the same thing, fixed effects or random effects. The only difference is that random effects are going to do this partial pooling thing. So they're going to pull everything sort of closer to that mean. So if your average intercept is 100, right? And then you have one teacher who their score is 110, and it's like way out there because most people's is say like between 100 and, or between like 95 and 105. Then you have this really far outlier. It'll pull them closer to 100. So instead of being 110, it might pull them down to like 108 or something like that. That's called partial pooling. It was one of the topics I thought about covering in class, but I don't think we will. Any other questions? Okay. So that was a big part of what I was trying to communicate last time, and hopefully that makes it a little bit more clear. The plotting part is the other big part, okay? And I'm going to talk this time about this function expand.grid as a way of creating different conditions from which you might want to make predictions, okay? So let's compare the slopes across the first 5 classrooms. Okay, so we're still predicting for our sample here, all right? So what this expand.grid function does is it takes arguments and it basically, so it'll take 2 columns, 2 vectors, and then it's going to expand them so that you have every combination, every possible combination. So here I have xtrav is 1 to 10 and class is 1 to 5, all right? So for every class, we're going to get xtrav 1 to 10. So it's going to go 1 to 10 for class 1, 1 to 10 for class 2, 1 to 10 for class 3, etc. Okay, so if I look at head for conditions, you can see xtrav is varying and class is constant. And then if I look at the tail, you'll see xtrav goes to 10, and this is now for class 5. Okay, so overall, this is, 50 rows or whatever. What we can do now is, right, so this is the extroversion score for just some generic student, right? It's not like a student in our class. It's just some random generic student, okay? And then we have the classrooms 1 to 5, okay? And we have those random effect estimates for those classrooms, right? And we're saying, what would we predict for a score for a student in this classroom with this extroversion score? Okay, so our data frame looks like this again, right? Xtrav 1 to 10, 1 to 10 for class 1, 2. I should have gone 0 to 10, but I didn't. And then we're going to say, okay, predict from my model what we would get for these data. Okay, and all this is going to do is it's going to run through this sort of thing here for each of these, right? It's going to pull the random effect estimates for class 1, and then it's going to multiply this times the fixed effect estimate, and then we get a prediction for those things. But notice this is not like real data, right? These are data I made up. But of course, we have kids that scored in these ranges, but this is not a score for any one kid in our data set. All right. And the reason that that is so useful is because then I can produce plots like this, where we don't have any missingness here or anything. So I'm saying this is my model predictions for an extroversion score ranging from 1 to 10 across these first 5 classrooms. And part of what we see here very clearly to start is that negative correlation between the intercept and the slope. If you recall way back when I showed the different, the model, right? The correlation between the intercept variance and the slope variance was negative 0.97. And by plotting the first 5 classrooms here, you can see that very clearly, right? They're starting at different places, but they're all converging to the same place as we get to high extroversion scores. And so this really helps you understand what that negative correlation means. And rather than just seeing negative 0.97, you actually get a visual picture of it, right? So this is how, this is, as I've mentioned a couple of times now, making predictions from your model can really help you understand your model. This is part of what I mean by that. Okay.
Is this
Yep.
Is this something like Matthew effect fan close thing here when we are predicting? I mean, we learned that in the last HLM one.
Yeah, can you say it one more time?
It's Matthew effect where when we predict these models, we see what is happening. The gap is closing or gap is, widening.
Yeah. It's sort of related. It would depend on the, in this specific context where we're talking about popularity of kids and extroversion, I wouldn't probably describe that as a Matthew effect. But yes, depending on the specific context, if you were looking at, say, socioeconomic status and achievement or something like that, then you could have these sorts of things that you could see where like kids who are in the, although this is almost like the opposite of that, right? Like kids who start low progress more and kids who start high progress less, right? But you could get like a fan in the opposite direction. So kids who start low progress less, kids who start high progress more. And that would be more like a Matthew effect. Does that make sense?
A quick question too. So the conversion here, does it suggest that once you have a very high extroversion score, it doesn't matter which class you're in?
Yeah, it doesn't matter much. I mean, you can see there's almost no variance up here. There's a lot more variance down here, right?
Thanks.
Okay, one more quick example of this sort of thing, just to show how this can be useful. We're now fitting a new model where we're modeling the interaction between extroversion and sex, okay? I'm not allowing that interaction to vary by classroom. I am still allowing the extroversion slope to vary across classrooms, but the extent to which that slope depends on sex is going to be fixed across classrooms, okay? So here's the coefficients. And then here, now we might want to model the marginal effect, okay? So what I'm doing here is I'm doing expand.grade again. I'm saying extroversion is 1 to 10, sex is girl and boy, and class is 0, okay? Last time I did negative 999, you could do that also. Anything that is not in your data, okay? And what this is going to do is this will give me 1 to 10 for girl and class 0, and then 1 to 10 for boy and class 0. Okay, and then I'm piping that directly to mutate, where I'm creating a new column, and you could do this in separate steps or all in the same, it doesn't really matter, where I'm saying predict from M2, where the new data is dot, okay, and the dot is just a placeholder for when you're piping. So when you're piping like this, the dot means the data that I just piped in, okay? So new data is going to be this data, okay? If that's confusing, just do them in separate lines like I did on the previous one. But then I also have this additional argument, allow.new.levels, okay? And what this is going to do is it's going to say, don't worry about the random effect estimates, just use the fixed effects, okay? And then I get something that looks like this. So here's the extroversion score for girls in any classroom, right? It's not for a specific classroom. And then here's the extroversion score for boys and then our prediction for both of them. And then we can plot them like this, where we're saying that data frame I just created, put extroversion on the x-axis, prediction on the y-axis, and then color them by sex, and we get these two different slopes. And you can see, like, we could look back at the coefficients, and we can see that this is a pretty small estimate, but we also can see it visually here that they're basically parallel. Okay, so girls have a higher popularity on average, but that the relation between extroversion and prediction, and not prediction, extroversion and popularity doesn't really depend on sex. Okay, so this is a marginal effect because it's not for any specific classroom, and we're sort of averaging across classrooms basically, and then we're looking at the relation between how our model would predict boys versus girls as a function of extroversion for popularity. Okay, any questions on that? That was really, I mean, it was a lot quicker, but that's basically the main sort of take-home parts of last lecture that I really wanted you to get. And like I said, I wanted to spend the time here because I felt like last time, especially by the end, there was just a lot of not knowing what the hell is going on sort of thing. And that, you know, I don't want that to be the case. Like, obviously, if I'm producing the materials and I'm covering it, then I want you to get it, right? It's not so hopefully that clears it up some. But are there any other questions before we move on? Okay.
No questions, just a comment that this is first time I have understood some of the things. So thank you very much.
Oh, good. Good. That makes me happy. All right. Let's go ahead and take a 5-minute break now then. So come back at like 10:50. Let's do 10:56. Okay. Okay. So today, for the rest of today, we're going to talk about the Gelman and Hill notation and contrast it with Raudenbush and Breich. And then we might get into the variance covariance stuff a little bit, but we only have an hour left, so there's no way we're going to get through all of it. Okay. All right. So again, going back to standard regression, which I like to think as just sort of always our baseline. We can think of like if we had a model like this, right? So this is the model that we're fitting, where we're having miles per gallon is predicted by engine displacement plus horsepower plus drag ratio, right, from empty cars. We would probably display that model like this, right, or something close to this. We might use beta 0 instead of alpha, but whatever. It's basically like this, right, where MPG is predicted by these things. What we often don't show is the distributional assumptions of the residuals. So this model also has this built into it, right? So our error structure is assumed normally distributed. So distributed as, that's how we read that, right? Distributed as normal with a mean of 0 and some unknown variance or standard deviation. Okay, so this is estimated. This is our residual variance, right? A different view of the same model would be to display it like this, right? So we have y hat, which is given by all of this, and that actually gives us our mean for this thing, okay? So now we're saying our outcome, MPG, our miles per gallon, is assumed distributed normally with some mean structure y hat and some variance that we're going to estimate. Okay, and then that mean structure y hat is modeled by some intercept that we're going to estimate, plus the relation between engine displacement and miles per gallon, etc. Okay, so then basically what we end up doing, we could break this apart, but we end up having essentially like multiple, like the mean structure here is going to depend on these variables. All right. Now, this notation is maybe a little bit different, but it definitely makes the distributional assumptions a little more clear, right? So this model is literally the exact same as this. It's just this part we typically omit, right? That part just is not usually shown. And in this notation, we're now showing that very clearly. But otherwise, it's basically the same thing. We're just saying the mean structure is going here. Okay. So each MPG value is assumed generated from a normal distribution with a mean structure according to this and some unknown standard deviation, which we will estimate. Okay, I'm not expecting you to follow along here, but part of why this notation is useful is because if you want to estimate, if you want to simulate data from a model, then it's a lot easier when you see all the parts of the model, right? And nothing is missing. So I'm going to walk through this really quickly. Let's say we wanted to estimate data from a model just like the one that we just showed, okay? Or I want to simulate data. So I'm going to just make up some stuff here. I'm going to say n is going to be 1,000. So we're going to simulate 1,000 observations. We're going to say the intercept is 100, and beta 1 is 5, beta 2 is -3, and beta 3 is 0.5. Okay, and then sigma, my residual standard deviation, is going to be 4.5. Okay, again, just totally made those up. Next, we can simulate some vectors that we're going to multiply by our coefficients. So I'm using set.seed here to give me reproducible results. And so I'm using 1, 2, 3. So if you wanted to simulate the results I'm getting exactly, you could use set.seed 1, 2, 3. So first I'm saying x1, x2, x3, right? These are going to be our predictor variables. And I'm saying r norm n. So I'm saying simulate n, which is 1,000, observations from a random normal distribution that has a standard deviation of 1. Okay, and then the mean is going to be 0 by default. This one's going to be a standard deviation of 2, and this one's going to be a standard deviation of 4. The standard deviation here will relate to the standard error. If we have more variance in our predictor, then we're going to have lower standard errors because we'll be able to estimate it better. Okay, now we're going to create y hat. So y hat looks like this, where we're going to say the intercept, our intercept, which was 100, right? Plus b1 times x1 plus b2 times x2 plus b3 times x3, right? So that's just the mean structure that I had before, but I'm doing it now with my made up data. And then I create this thing called sim, where I say sim r norm n, so get n observations, where the mean is equal to y hat, and the variance is equal to sigma. The standard deviation is equal to sigma, which is 4.5. Okay? And now here, I'm going to say, okay, now let's fit a model to that. So I'm just calling summary directly on LM, where I'm saying sim x1, x2, x3. Okay? So what you can see here is when I actually estimate a model from this data, I get down here an intercept estimated at 99.96. X1 is estimated at basically 5. This is estimated at basically 3 and basically 0.5, right? These are all the things that I set. And then my residual standard error is 4.46, very close to what I set. Okay? And I'm able to create this simulated data in a pretty straightforward manner because I can see all the distributional assumptions. So I'm just basically walking through this and making up stuff for this, 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 and this. Okay, and then I just combine them like that and then say, okay, now give me data from a random normal distribution that has that mean structure with that variance. Okay, so that's helpful, I think. Oops. But we can generalize that same sort of an approach to multi-level models. Okay, and again, I think this is helpful because it helps us understand the error structure when we have more complicated models. And when I say error structure with a multi-level model, that's going to mean the random effects variances and covariances also, not just the residual variance. Okay, so using this same sort of an approach will help us understand the distributional assumptions of our model better. Okay, here's a simple example. And again, I know we're all sick of HSB, but whatever, it's just a quick example. So I'm using LME4 and I'm using Equasiomatic because that has the HSB data set. Okay, I'm fitting a model that looks like this. So I have math is predicted by SES score, and then the intercept is randomly varying across school IDs. Okay. In Raudenbush and Breich notation, this model would look like this, right? So we have math score is predicted by beta 0j plus beta 1j SES. So SES is our level 1 predictor, right? Plus EIJ. And then each of these coefficients are modeled at this second level. So beta 0j is modeled by gamma 00 plus U0j. So U0j is now our random effect, right? Estimate. So we're saying that this intercept, B0j, is randomly varying across schools. And then B1j is equal to gamma 10. And there's no random effect here because we're just saying that's going to be fixed across schools. Okay? But again, just like in simple linear regression, what we typically don't show is the distributional assumptions here. So this is not always the case, right? Sometimes people show this, but a lot of the time they don't. The expectation of EIJ is 0 and the variance is sigma squared. Expectation of U0j is 0 with a variance of tau 00. Put slightly differently, EIJ is assumed normally distributed with a mean of 0 and some unknown variance that we're going to estimate. Okay, U0j is similarly assumed distributed from a generated from a normal distribution with a mean 0 and some unknown variance tau 00 that we're going to estimate. Okay, and if you put it all like this, then everything is there and it's pretty clear. The Gelman and Hill notation sort of skips that step and just puts everything in a normal distribution to start with. So very much like we did before with the simple linear regression, we're going to say that the outcome, whatever our outcome is assumed generated from a normal distribution with some mean structure. Okay, the difference is, and then some unknown variance. The difference is those parameters in that mean structure themselves might be generated from a different structure. Okay, so here we have AJ, alpha J, alpha Ji. That means that alpha, our intercept, is randomly varying across something. Okay, whereas beta 1 is just beta 1, so it's just fixed. Okay, and we can see now this alpha J part is down here. So the alpha J, we're saying there's a different alpha for each, and we can look down here to see what it is, school ID. And the distribution of those alphas of the intercept, the distribution of those intercepts are themselves assumed generated from a normal distribution with some mean and some standard deviation. Okay, so basically what we're saying here is this part is very similar to the different way of looking at it with simple linear regression, right? The difference is that in that mean structure, we might also have other parameters that are varying randomly, and those have their own distributional assumptions. Okay? So this notation, I think, communicates the distributional assumptions in a little bit more clear manner. So we can also pretty easily see what level the predictors are at still, because this is the school level and we're just saying a mean, whereas this is the student level. So student level, we have an SES predictor, okay? And we'll see this more as we continue on. So this model does look a little more complex, and it's probably going to take some getting used to, but the Raudenbush and Breich notation is also pretty complex, right? And one of the things that I dislike about the Raudenbush and Breich notation is that as you start to build up more and more complicated models, your model equations can take up like literally an entire page or more, because every single coefficient has to have its own new definition, right? And so it just kind of explodes as you get more and more. Even like, let's say you fit a 4-level model, which is pretty complicated, right? But even if you have like only one predictor in the model, but it's 4 levels, it will be so long, right? Because every single one has to have its own definitions. And this sort of avoids some of that. It's still going to be a big equation, but it won't be quite as big. And similarly, if we understand what all of this is saying, then we should be able to simulate data from assuming this model is true more easily. So this is sort of a bonus. It works actually with Raudenbush and Breich too, but we can communicate the model results using this pretty well as well. So we're saying our math scores are assumed generated from normal distribution that have this mean structure. So 12.66 plus 2.39 times SES. But this 12.66 varies between schools, and we're saying it has a mean of 0, which is just to say it has a mean equal to this thing, for school ID J1 to J. Okay, so the standard deviation in school intercepts is 2.18. Okay. Extra bonus, Equasiomatic is my package. And what it's used for is to extract equations from models. And as I've mentioned, I prefer the Gelman and Hill notation, so that's the notation it uses. There's other reasons I prefer that too. Specifically, we will get to generalized linear mixed models later. So basically, you know, like having binary outcomes or possibly count outcomes or things like that. Equasiomatic doesn't currently handle those, but it will hopefully soon. But the main thing that is nice about this is part of the reason we chose Gelman and Hill notation. This notation generalizes to those other models pretty straightforward, in a pretty straightforward way, because we're basically just changing what the distribution is. Instead of saying it's generated from a normal distribution, we might say it's generated from a binomial distribution, right? So, so what's nice too is if you want to use a Gelman and Hill notation, which I would encourage you to, you can get that model equation for any of your multi-level models at this point that have continuous outcomes by just using this function extract EQ. Okay, so we extract EQ from HSB M0, and in this case, if I want the actual estimated coefficients, I would just say use coef equals true. Okay, it also will work for simple linear regression models and ordinal regression and a bunch of other models, but we just haven't incorporated any linear mixed effects regression models except LME4 Elmer at this point. Okay, but that is cool too, I think. I'm a little bit biased. All right, so let's very quickly talk about simulating data from this distribution. Okay, so, or from this model. So I'm not gonna like spend a ton of time here because the code is fairly complex, and hopefully we will get to this at some point through the term, but I'm actually thinking probably not. So we may or may not go over this in more detail later, but I want to give you the general idea regardless. Okay, so first we're going to set some parameters. So I'm saying J, which is the number of schools, is going to be 30. And then I'm saying NJ, which is the number of students per school, is equal to 50. And I could make this more complicated, so I have a varying number of students per school or whatever. But just for making this as simple as possible to start, I'm going to just say, okay, I want just the same number of students per school. Okay, then we're going to simulate the school distribution. And there's a couple of different ways we could do this. We could start with the fixed effects in here. So like, let's say we wanted the intercept to be, 58. We could say R norm J 58 with some standard deviation. But here, I'm going to do it the opposite way. I'm going to put the fixed effects at the first level. And so for my school distribution, I'm just going to simulate them around 0. Okay, so I'm saying give me J draws from a random normal distribution with a mean of 0 and a standard deviation of 2.18, because that's what I estimated before. Okay, and I'm storing this in an object that I'm calling AJ, alpha J. Okay, now this part's where it gets a little bit more complicated. I did it in a for loop because I think for loops are a little bit easier to kind of see what I'm trying to do, but then some of the code is a little bit more complicated too. But basically, these are just like creating empty things that I'm going to store my results in. And then this is the real heart of it, okay? So I'm saying for I in 1 to j, so this is j is 30, right? So this is just going to be a vector that goes 1, 2, 3, 4, 5, 6, 7, up to 30, okay? And then I'm creating an SES vector here, where I'm just taking nj draws, which is 50, right? 50 draws from a random normal distribution that has a mean of 0 and a standard deviation of 1. Storing that in SES. Then down here, I'm saying for the first school, simulate nj draws, so 50 draws, from a random normal distribution that has a mean structure that looks like this, right? 12.66 plus 2.39 times this SES that I just created up here, plus AJ, okay? So plus my school difference there. And that has this overall residual variance, 6.09. So it's going to do that for the first school, then the second school, then the third school, etc. Okay? If this isn't super clear, like why I'm using double brackets here and single brackets here, don't worry about it. It's not that important for now. The main part I want you to see is this, right? So this is like the equation part for a given school. So we have like the fixed effects here, and then we're adding in the individual school level deviation, which was simulated from a random normal distribution. And then all of this is coming from a random normal distribution that has a standard deviation of 6.09. Okay, then we can put it in a data frame. There's multiple ways to do this, but this is one way. And again, don't worry about the code too much. I'm trying to think about this more conceptually versus code-wise. But here we have a given school, and we have the SES scores for the students in that school, and then we have the score for the given student. Okay, so we can test it out just like we did before, where we now fit this model, but notice I'm using SimDF here instead of whatever model I was using before. And we can see everything ends up working just like we would have hoped. We have an intercept of 12.39, SES fixed effect is 2.46, 12.66, so maybe a little bit different, 2.39. This is 6.01 and 2.4, right? 6.09 and 2.18, so pretty darn close. And yeah, that's basically it, right? So we can see we've simulated data from that distribution, and it's not going to be exactly the same because it's simulated and it's randomly drawn, but you can see everything is quite close to what we would have expected based on the way that we simulated it. Okay, and so part of you might be like, well, that's weird. Why would I even want to simulate data? And there's a lot of different reasons why. One is that if you're doing any sort of methodological development stuff, you very regularly want to know what are the like true parameters, and then you build your model to see if it can recover those parameters that you set as being true. The other thing is, I really think, again, like I was saying, sort of with doing the model predictions, if you can simulate data from the model that you're fitting, you will understand the model quite a bit better than before having gone through that process, because it will force you to be like, wait, why am I doing this? And then why are the results not right and whatever? And it'll force you to go back, and then it's like, oh, I need to add these things together, or I need, whatever. And so I don't think we'll probably cover that. We might, but I do think that that's a really good process to go through. The last thing is, it can also help you understand, and this is what we were kind of going to do, it can help you understand the assumptions of your model a little bit better. Because maybe, let's say, in this case, I recovered the parameters pretty well. But let's say going back here, rather than drawing it from a random normal distribution, let's say I simulated it from like a Poisson distribution. So it's really skewed, right? Or something, some other distribution. Then I could look at my data that I simulated, fit this same model, and see if it still recovers those true parameters or not. And sometimes you'd be surprised at how well it works and how robust these models actually are to all sorts of different violations that we're taught really matter a lot. But other times it's like, oh no, this actually really matters, and now I'm not able to recover those parameters at all. Okay, so it's just a way to, again, sort of dig into models and understand how they work better and build some intuition about how they're working. Okay, so still focusing on notation.
Sorry, can I ask a question?
Yep.
So would you mind like sharing a little bit quickly, like overarching like workflow when you would would like to test if the model is doing good? You fit the model, you take out the parameters and then simulate based on those parameters and then fit the model again?
Yes. So basically you would set some like true population parameters for the model, right? And then what I would do if I were doing like methodological development is, rather than just simulating it once, I would simulate it like 1,000 times. So you'd have 1,000 different data sets all generated from the same like sampling distribution, right? So they're all generated assuming the same sort of thing. And 1,000 is maybe too many, but it depends on what you're doing, right? And the reason that you want to do that is because that gives you an idea of the sampling distribution too, not just a one-time thing. Because as we just saw, right, I didn't hit it exactly right. They're very close, but they're not exactly the same. And that's just because of random sampling variability. But because of the central limit theorem, right, of course, if we do this a whole bunch of times, we would expect that on average, it would be exactly or darn near exactly, right? So you would do it like 500 times or 1,000 times or whatever, and then you would fit whatever model you're doing, whatever sort of manipulations you're doing to all 1,000, and then sort of average across those to see if you're. And it also helps with doing a bunch of samples like that. It also helps you understand things like the variability in your estimator or whatever it is that you're testing across those samples. And last thing, but you can also, as you're doing those different samples, you can also say like, okay, I'm going to do 100 with a sample size of 10, 100 with a sample size of 100, and 100 with a sample size of 500 or whatever, and vary different things like that. And then you can understand like sort of conditions when your model's working really well and conditions when it totally fails. Does that help?
Yeah, thank you so much. And then we will also covering like how to the model diagnosis as well. Like,
yeah, we're gonna have to build in some model diagnostic stuff at some point. I don't have it currently. I was going to do it during that same time we were doing the simulation stuff, which probably would have been too much information in 1 week anyway. So maybe it might end up being that we just mostly cut the simulation stuff, but then we do talk about model diagnostic stuff.
Yeah, thank you. Thank you.
Okay, so expanding the notation, focusing just on the notation right now still, let's add a school level predictor, okay? So HSB still, we have this school level predictor called sector, all right? Which is, I think, like public-private, okay? So that is only varying across schools, right? So within a school is either public or private, and it's not going to vary within a school, so therefore it's a school level predictor. If we wanted to see what this model looked like, again, we can use extract EQ and it will just work like this. So now we have math I is assumed generated from a normal distribution with alpha Ji. So alpha is going to randomly vary across some level, and we can see because there's only J, it's only one level that it's going to be randomly varying across. And then we've got SES as a student level predictor, right? And then some variance. And then alpha J, our intercepts, are assumed generated from a normal distribution, which itself has its own mean structure, okay? So this is like the average mean or whatever, but then we're also adding in a sector coefficient, right? So this would be like, if we have public and private, this one would probably be like the reference group. So say this one's public, and then this would be what we would add in if the school is private. Okay, and then we have some variance. Does that make sense?
Can I ask you an application question about extract? And that is, when I use extract, I get down in the console, I get the $begin till, do I just copy that and then paste it outside of a code chunk and then knit it, and that's when I get the equation?
No. So if you're using this in R Markdown, you just do this. It's going to just write that code in a code chunk, and then it's just going to spit out the equation just like that for you when you knit it.
Okay, so I don't need to copy that code out of console and do it. It does it automatically.
It does it automatically.
Okay,
yeah.
Thank you.
So if you want to modify the equation at all, like let's say you wanted to change, this to actually say school instead of sch.id, then you could extract the equation, put it in your console or whatever, copy and paste that in, but then you would want to comment this out so it doesn't run when you knit it. And then you could just change the equation from there to be whatever you want it to be.
Great, thank you.
Mm-hmm. Okay, adding random slopes. We have sort of seen this a couple times now, but this is the other part where it's very rarely shown with the Raudenbush and Breich notation. And this is true across most estimation processes, right? But when we're estimating a random slope, we are also estimating the covariance between the intercept and the slope, okay? Or as it's shown here, the correlation, all right? So this shows that as well, okay? So here we've got SES plus sector, and then SES is randomly varying across school IDs as well as the intercept, right? So now our model looks like this, which again, it looks fairly complicated, but you can walk through it and hopefully it should make sense. Okay, so we have our math score is assumed generated from a normal distribution that has this mean structure, and we've got alpha J and beta J. So both the intercept and the slope are assumed randomly varying across school IDs. Okay, and then we have some residual variance here. Now, down here at the school ID level, we actually have a multivariate or a bivariate normal distribution. So we have alpha J and beta J are assumed generated from a joint normal distribution where the intercept mean is shown here, and the slope mean is just whatever the average slope is. So this is kind of like Raudenbush and Breich, except this is only for the fixed effects, okay? And then this mean structure is assumed randomly varying according to these variance components. So we have a variance for the intercept, a variance for the slope, and the covariance between them, which is both of these terms. They're the same thing. Okay? So again, it's like we're not just saying that we have some intercept variance and some slope variance. We're saying we have this like joint variance that's all coming from the same distribution. Very often we also want to include interactions. Okay, so now we're just getting more and more complicated. You don't have to fit these models or anything, but if you wanted to, you would have to probably use the dfoptim, have it installed. You shouldn't have to load it, but you should have to have the dfoptim package installed, which is what I sent an announcement about in case you did want to run this. But this is just so that we don't get convergence warnings. And I did that using the all fit function and inspecting the different optimizers, right? But here now I'm saying sector time, or SES times sector, right? And then SES is randomly varying across school ID. And so now we have alpha J and beta 1J here. So this is all still the same. But now at this level, we're saying our intercept, right, is predicted by a school level predictor for sector. But also our slope, beta 1, is predicted by a school level predictor for sector. Okay, so again, this would be like, this is the slope we would expect for public schools, and this is the slope for SES that we would expect for private schools. Okay, so again, this is quite similar to Raudenbush and Breich in terms of how the layering is happening, because this is a predictor of this slope, which is an interaction. And that part of, and then all the rest of this is the same, but this Equasiomatic will figure out for you what level things are at. So it figures out that sector is a school level predictor, but it'll also figure out those interactions. So it'll figure out that sector is a predictor of SES. Okay, and that's really actually, I think, a super helpful way of thinking about interactions generally. You have some basic, like baseline slope for SES, but then you also have a predictor of that SES slope, right? Which is what an interaction is. Does that slope depend on some other variable? Okay. And I'm guessing for most of you, like this sort of bivariate, and it can get more complicated, as we'll see in a second, but it might feel kind of uncomfortable because it's like a lot of notation and everything. But as you start to work with it, hopefully it'll start to feel more comfortable. It is showing the same things, it's just showing them in a more complete way, basically. All right, so here I've now added a bunch of other stuff. So we've got SES times sector, just like we did before. But now I'm saying plus minority plus female, those are both student level predictors. Plus mean SES plus size, those are both school level predictors. And then I'm saying SES and minority and female are all varying across school IDs, okay? This model doesn't actually fit. I omitted some convergence warnings that I didn't spend a lot of time, but I couldn't get them to actually work. But I just wanted to show you this, okay? By default, and you can change this, but by default, Equasiomatic will actually break out the mean structure for level 1 if it gets too long like this. I probably need to build that in for level 2 and 3, but I haven't done that yet. But so this is saying math is now predicted, or not predicted, is assumed generated from normal distribution with some mean mu, and that mu is equal to this mean structure. Okay, so that's just like with simple linear regression. And then you can see these, you know, these are all predictors of the intercept, these school level ones. So they go on that intercept level. And then we have sector still that is predicting the slope variance, but we don't have anything else that's predicting that minority slope or the female slope. So those are just means. And then we have this huge covariance structure over here, right? And so when you see something like this, it makes more sense why this model is having a hard time estimating, right? Because you're not only estimating each of these variance components, you're estimating all of these covariances as well. And that's just a lot to estimate, because now you're estimating, you know, random deviations for every single school for, you know, SES, minority, and female, as well as the way that those things go together. And so this is where a model can become can start to become overfit to the data. All right. But even if it's not overfit, you might have a hard time getting your model to converge. And so you sort of have to make compromises here. Part of the compromises are things that we'll start to talk about here in just a few minutes in terms of simplifying that covariance structure. But the other thing is you can make compromises like, well, okay, theoretically, I could see why the minority slope in this example would vary randomly across schools, but there's just not enough variability in my data set to estimate that. So you can talk about that in your paper, right? Like you'd say, although theoretically you could think of reasons why the minority slope might, obviously you'd be a little more, professional in your language, but like you could see why that might randomly vary, but there wasn't enough variability in our data, and so we assumed that it was fixed because we ran into convergence warnings if we tried to model it as random, right? Okay, last one for the different notation, right? We're going to look at the sim longitudinal, and then we're going to model a bunch of different levels. So I'm going to go to a 4-level model, okay? So here, this is a big model, right? And it, again, doesn't really fit. But we have wave times treatment plus group plus proportion low, okay? So prop low is a school level variable, and then treatment is a student level variable, and wave is a time level variable, right? So it's a within student level variable. So this is at level 1, this is at level 2, this is at level 2, and this is at level 3. But then we're also estimating intercept variance at level 4, which is district, okay? So we've got wave varying randomly across students, wave plus treatment randomly varying across schools, and then the intercept varying randomly across districts, okay? And so then down here with our equation, we have score is assumed generated from a normal distribution that has this mean structure. Notice we're saying alpha j k l. So rather than just alpha j, now we have j k l. It's randomly varying across those 3 levels above level 1, right? And beta 1 is randomly varying across jk. So not L, but jk, right? So that's going to be SID and school, but not district. Okay, and the only level 1 predictor we have is wave. Okay, at level 2 we have the student level predictor, and this is going to be their intercept, like the things that we're using to predict students' intercept, and this is what we're using to predict their slope. So you can see, because we've got wave times treatment, we've got treatment predicting their intercept and treatment predicting their slope. Okay, the group is low, medium, and high, and so we have low and medium with high as the reference group, and that's just predicting their intercept. And then we only have wave and the intercept and wave varying across SID, so we get this random effects variance structure, right? 2 variances, 1 covariance. At the school level, right, we only actually have 1 variable at the school level, and it's only predicting the intercept. So we have alpha, beta 1, and gamma 1. So because we have wave and treatment, right, we have wave randomly varying. But notice here we have treatment within this level 2 has gamma 1k, right? So gamma 1k comes down here, right? And we have beta 1 also. Okay, so treatment is the main effect for treatment is randomly varying across schools. Okay, the interaction for treatment on wave is not randomly varying. Okay, I know this is a lot, but this is a really complicated model. So then we have these 3 things are randomly varying across schools, as we can see up here, wave, treatment, and then plus the intercept. So wave, treatment, right? And so the intercept variance, or the intercept is predicted by the proportion low, that's this, right? And then these are just means. And then because we have 3 things randomly varying, we're estimating each variance as well as the covariance among them. Finally, at the school or at the district level, we just have alpha L is assumed generated from normal distribution with a mean mu alpha and some unknown variance. Okay, so I know this one is really complicated and probably would be really difficult to fully parse. But I wanted to show you a complicated example at the end, just to show you how this notation generalizes to more complex models. Okay, generally, I think your models are probably going to look closer to this sort of thing, which hopefully makes sense. And if this one is feeling, or that one might be a little bit tough, but if this one's feeling like totally lost, that's okay, right? So Tyler was talking about in the chat about being able to see what level things are at. It is true that with this, you can't really see that what level this is at, and you do kind of have to keep track of it. But the other thing that is nice about it is you don't have to have data sets for each level either. You just have one data set, and if something, and you can put that in the name too, right? Like you could call this SCH prop low or whatever. And stew group or whatever. But then you can also use the extract EQ to help you out here in terms of, because it'll figure it out for you in terms of what level things are at. Okay. But yeah, I'm not, again, this is maybe a little overwhelming and this may not totally make sense, and that's fine. But I did want to show you how it generalizes. What I'm hoping more is that you understand basically like how this is working. Okay, so that should be sort of where your focus is. And then I would encourage you to try Equasiomatic and extract EQ and see if you can understand the models. Okay, as we go forward too, I will start to actually probably just show you a model and have you have a data set and see if you can fit it. Okay, and it'll just be like a quick, go ahead and try to fit this model, and then we'll go over it as a class how to do it. Lindsay?
I just have an R related question. Do you only use set seed when you're using simulated data?
So you use set.seed anytime you're doing any sort of random process. So if I'm randomly sampling data, or I'm randomly generating data, or anything where I'm doing anything that is random, I use set.seed, because what that does is it basically just makes that randomness reproducible. So like if I said rnorm 5 and I don't use set.seed, every time I do rnorm, I'm going to get a different result. Whereas if I do set.seed 1, 2, 3, rnorm 5, I'll get a set of results. And then if I do set.seed 1, 2, 3, rnorm 5, I'll get the exact same 5 results again.
Okay, that makes sense. Thanks.
Mm-hmm. Any other questions?
I have one about the model that you ran. You have this interaction of wave by treatment, and then you have the wave plus treatment as a random effect, as both as random effects. Did you have to do that because you had an interaction, have both of them? And can you also put an interaction term as a random effect?
Yes, you can have an interaction. So the first part, no, you can have an interaction without it being random. That's totally fine. The notation will look different, and I actually just had somebody file an issue with Equasiomatic because they didn't understand. But the equation will look different, right? So like if I didn't have this randomly varying here, like wave was not randomly varying across SID, then I wouldn't be able to have treatment as a predictor there, right? But if I could still have wave times treatment here, and it would just be here. It would just say wave times treatment, right? Because it's basically an intercept level predictor then at that point. So that's the first part. It doesn't have to be randomly varying, and you can still model the interactions. Then the second part, what was the second part?
If you can have a random effect of an interaction.
Yes. So you could, for sure, and so, theoretically, that would mean like that. So in this case, the extent to which students grow over time depends on treatment. And so then you would be saying that that relation, right, depends on school also. So which would make some sense because maybe you have schools that implemented with high fidelity and other schools that didn't. And maybe you didn't have a really good fidelity measure, but you wanted to sort of account for that. So then you could model that interaction as randomly varying across schools. What I will say though is generally those models are going to be really tough to estimate because there's just generally not going to be that much variance in an interaction across levels. So it might work, but most of the time in my experience, it doesn't work. So you have to have quite a bit of variability for you to be able to estimate it with any sort of precision.
Thanks.
Yep. Any other questions?
Just a clarifying question. When we want to estimate or perhaps like estimate the slope, randomly varying slope at the school level, are we gonna include like we have the gamma 1K down there in the third chunk? Yeah, if we wanna predict something, we include that. How are we gonna do in the R code? Like, are we gonna include another thing in the like wave treatment protocol, like the school stuff?
Yeah, so this is the other part of thinking about models through this multi-level structure is mostly really helpful, right? It's mostly really nice to think about what predictors are at what levels and how do things randomly vary across levels, and you have this nested structure and everything. But it can be occasionally a bit limiting. And I think this is an example of where it is a bit limiting because I think we end up getting so caught up on what level things are at that we forget that what you're talking about is just an interaction. It's an interaction like any other interaction that exists in simple linear regression or anything else. And so all we'd have to do is, so gamma 1 is treatment, right? And that's randomly varying at the school level. Let's say I wanted to have the proportion low predicting the treatment effect. I would just model the interaction between prop low and treatment, and that's it. That make sense?
Yeah.
So when you're including interactions, they sort of parse out in the equation according to their levels, like what level they're at, but they are just interactions, just like any interaction.
Right. Thank you. Yeah.
Any other questions? Okay, so we are going to probably mostly just cover this next time because we only have 13 more minutes. But I will I'll get through what I can in the next 10 minutes or so here, okay, which is, I'm not going to rush, but I can at least hopefully introduce this concept. And then I'll send you an announcement later, so be looking for that, but then we'll talk about how we're going to update the schedule. I mentioned a couple of times that it's kind of hard coming in as the instructor of the second course, not knowing sort of where you all were at the end of the first course. And then there's a lot of variability in comfort with R and a lot of variability in comfort with multi-level modeling. So trying to find that balance has been challenging. I feel like we've done it pretty well today, and I feel like we pretty much failed last week. So, we're moving forward. I'm gonna need to adjust the schedule to sort of account for this, and we'll probably have to do that a couple more times. So, I mean, hopefully not, but so yeah, just hopefully you can be a little patient with me there. But so I'll introduce this here, and then this will mostly be the topic for next week. Okay. Okay, so the data, we're going to work with this data from Willett from 1988. It's 35 people, so this is a link to the article. Each completed a cognitive inventory of opposites naming, and then at the first time point, participants also completed a general cognitive measure. Okay, So you can read in the data like this and go ahead and do that. Give me a thumbs up emoji once you got that. All right, good. Okay, now standard OLS, ordinary least squares, standard linear regression. Why, right? We might fit a model that looks like this. I'm just calling this model bad because it's a bad model. Okay, so we have LM OPP is the opposite, right? That's the outcome. And then we're measuring that by time. Okay, so if we look back at the data, time looks like this. It's just coded by wave, 0, 1, 2, 3. Okay, and that's it. So we're saying the data is Willet, and we get some estimate that looks like this, and time looks like that. All right. Why is this bad? Well, we've talked about this before, but this is what our model looks like, and we have this assumption for the error structure. You can think about this actually in terms of a multivariate structure. And this looks scary, but it's not that scary, I promise you. Just I'll explain it, okay? So if we took every student in our data set and we expanded it so they each have their own error, okay? 1, 2, 3 to n. Okay, so this is every participant in our sample, all 35 of them. We could assume that their error structure was generated like this from a multivariate normal distribution with a vector of zeros and then an error structure that looks like this, right? So every student has their own error. But notice the off diagonals here are all zeros, okay? This is standard OLS. This is what we do when we're modeling with ordinary least squares, with standard linear regression, okay? You might have seen in the past IID. It stands for independent and identically distributed. That's what this is, okay? They're independent, meaning all of these off diagonals are 0, and they're identically distributed because whatever this sigma is the same for all students, okay? So that's the assumptions of simple linear regression. Why is this so bad? Well, normally it's not, but in this case, we have the same student data across the first 4 time points, and then a different student's data across the next 4 time points, etc. Okay, so assuming that data from this time point is independent and identically distributed from this one, especially the independent part, right? That this residual here is going to be independent from this residual is crazy, right? Because it's the same student over time. So it makes no sense that the errors would be independent. They're not. They're going to be correlated because it's the same student. Okay. So a multi-level model really helps solve this problem. Okay. Very regularly, there's reasons why we would assume that the residual structure is not IID, including this one, right? We have 4 time points for each individual. So an observation for one individual at one time point is not going to be independent from an observation from the same individual at a different time point, okay? They're going to be correlated within an individual. So rather than estimating one single residual variance, which is what we do with OLS, we're going to estimate blocks of residuals, okay? So we're going to estimate a block of residuals for one student and then a different block for another student, okay? So this gives us this block diagonal structure. So this is the same sort of thing. Again, I know it's huge, but it's really not that different from what I just showed, right? Now our error structure, notice we have 2 subscripts here, 1, 1, 1, 2, 1, 3, 1, 4. So that's saying the first, second, third, and fourth time point for the first person, okay? And all of those, we get a block of variance components there for that first person. Then we move to the second person and we get another block, okay? The off block diagonals are still 0, Okay, so we're assuming students are independent and identically distributed. Identically distributed because, again, these variance components here, that first row, is going to be the exact same as this first row. Same as this second row is going to be the exact same as this second row. Okay, so that's the identically distributed part, and the independent part is the off diagonals. But within a student, we're not making that assumption. Okay, so we have these correlations that are estimated for the off diagonals, and then we have the same variance components for all blocks. And the out of block diagonals are still 0. So that block being the same for all students is what's called the homogeneity of variance assumption. Okay, so the residuals can be heteroskedastic and dependent within a grouping factor, which in this case is people, but it doesn't have to be people, right? In our HSB one, we would say the residuals are heteroskedastic and potentially dependent within a grouping factor, so within a school. But the entire structure, so the blocks, are repeated identically across units, so people or schools or whatever. Okay, so this leads to this block diagonal structure. And because of that homogeneity of variance assumption, we can sort of simplify that really big, really complex looking residual variance thing into something that looks like this, where we're saying R for our residual variance thing is assumed normally distributed with this bold 0 means basically a vector of zeros, okay, with this structure where this sigma R is equal to this. Okay, so now we're just saying sigma R is that block structure, and that block structure is repeated across all students. Okay, so this is what is often referred to as the composite residual. Okay, so let's go ahead and try. We only have 4 minutes, so I'll give you 2 minutes. Let's try to fit a parallel slopes model with the Willett data. Okay, go ahead and give that a try real quick. Okay, this is what it should look like. I'm calling it W0, right? So up is predicted by time, so that's just like our simple linear regression model. But then I'm saying plus 1 ID. Okay, so this is our random effects part, and we're saying that 1, our intercept, is randomly varying across IDs. Okay, with the Willett data. So what does the residual covariance for this variance covariance look like for this? This is where the sundry package, I just put this function in there like as I was producing these slides, but it can help you see that. Okay, so if you load the sundry package, hopefully you got that installed, you can pull the residual variance covariance. Okay, so that's what the function is saying. Pull the residual variance covariance for W0. And when we look at it, you can use image to actually look at what that looks like. Okay, so this is the student ID basically here. And then you can see if it's shaded, then there's a value there. And otherwise, it's not. The color of the shading is given by the value of the thing. Okay, so that diagonal is a lot darker than the off diagonals because they're higher values. We can also subset it like this. So I'm saying 1 to 8, 1 to 8. So I'm saying give me that composite residual for the first 2 students, basically, the first 8 time points. And you can see it is the same for both of them, right? It's exactly identical. But we also have the same variance across time and the same covariance for all of them. Okay? And that is because we have only estimated random intercept variance. Okay? So I'll talk more about why that is and how we can extend it, and then how we can extend it to other structures besides just an unstructured variance covariance matrix, which is the default if you have a random slope with LME4 next time. Okay? So that's it for today. Homework 2 is up there. It's not actually technically assigned yet. It'll be assigned next class. Okay? And I wouldn't expect that you'd be able to know how to do everything there, but you might want to take a look at it anyway because it might help you know what to kind of look for as we're going forward with the slides. Any questions, comments, anything you want to check in on before we sign off for the day? Okay, thank you all, and I will see you on Friday, next Friday.